Alright, so this is the chapter 23 quiz. Alright, first one, flat circular loop of radius. Okay, so this is radius. Alright, let me see. This is the radius, right? Okay, radius is rotating a uniform magnetic field. So this is a field. Find the magnetic flux. Okay, so what is magnetic flux through the loop? When the plane of the loop and the magnetic field vector r at angle 30. All right, so same thing here, right? So this is a loop. This is a field B, okay? And the plane of the loop, right? So this is the plane of the loop, plane, right? So this is a loop of the plane, right? This is 30. All right, so magnetic flux defined as, you see, magnetic field, area of loop, cosine theta. This theta is angle between magnetic field and normal to the loop, perpendicular to loop, right? If this is 30, this will be 60. So the angle here, you use the 60. Okay, so field here. What is the area? Area here is a circular loop, right? Radius is this. So area equal to pi r squared. Okay, so plug everything in. That's the answer. All right, second one, resistor and inductor. So resistor, inductor, right? Connecting series to an ideal battery. So this is an ideal battery. Okay, all right. Battery. At the moment the contact is made with the battery. Okay, so here the voltage across the inductor is, so this is the voltage, right, about here. All right, so the voltage here is same as this because the current is 0. You see, this is the time and the current, so this is ramp up. Okay, so at this moment current is 0. Just first make contact, current is 0. How to make current 0? So you have EMF here. So this guy give you induced EMF. This is induced EMF will be in opposite direction. You see? All right. So in this case, the net EMF in the circuit is 0. So the current here is 0. Okay. So the voltage across the inductor is equal to the battery's terminal voltage, greater than the battery, okay, equal to the voltage across the resistor, less than the battery is okay. So the A is the answer. Okay, but this is the magnitude, basically the voltage. All right. Number 3, the primary of an ideal transformer has, okay, so N1 equal to 100 turns, right? And the secondary 200 turns. N2 equal to 200 if the input current at the current I1 equal to 100A. We expect the output current at the secondary. Okay, so here is the equation, right? So V2 over V1 is N2 over N1. So this is voltage relationship. We also have power is the same, so which means N1, which means that I1 V1 equal to I2 V2. So you see I2 over I1 equal to V1 over V2. V1 over V2, right, equal to N1 over N2. Okay, so if primary is 100, secondary is 200, right? And so we can tell I2 equal to N1, N2, I1. Okay, N1 is 100, N2 is 200, I1 is 100, right? So plug in. You see, just plug in. All right. So you plug in. So this here. So this is 100, 200, then 100, right? So this will be 50. Okay, so that is this. All right, C, number 4. Number 4, a conducting rod of L25. So this is L 25 centimeter. Okay, remember 25 centimeter equal to 0.25 meter. All right. in a U-shaped metal, wire that is connected to the light bulb, having a resistor. So here, R equal to 8.0 resistance, okay, ohm. The wire and the rod are in the plane of the constant uniform magnetic field. So B here equal to 0.4 Tesla, 0.4 Tesla. Apply perpendicular, okay, so applied external force, pull the rod to the right, okay, so this is the force, okay, with a constant speed, so V equal to 6.0 meter per second. What is the magnitude of the EMF? All right, so just like from equation, right? So induced EMF equal to B L V. How do we get this? Okay, so actually I derived this in class, right? So I derived it in class. Okay, so this y equal to changing flux over time, right? So changing flux here equal to B is the same, right? Changing area and cosine theta here is 90, okay? This is the flux, right? So it's a field here and area, right? Perpendicular to the area, actually it's 0, right? So it's a cosine 0, right? So perpendicular to the area is getting into the screen, okay? Perpendicular, this is the area. Okay, so a field here getting into the screen, so it's a 0, and then delta t, and this equal to B, all right, B, and you see delta A equal to delta x times L, then delta t, right? Delta x over delta t is V. Okay, that's it. So you have everything. Just plug into the equation. You can figure out what is induced EMF. All right, number 5. The current flow through a circuit is changing. So changing current over time equal to 6.0 a second, right? If the circuit contains a 190 Henry inductor, what is the induced EMF? All right, so this one tells you that induced EMF equal to induced EMF proportional to changing current. The proportionality is inductance. All right, so you see you have inductance 190 Henry, and you have this 0.6 ampere per second. Put them together, right? So 190 and 0.6 time together is your induced EMF. Okay, so 6.0 second, 190 Henry. What is induced EMF cross inductor? Okay, so basically this is your induced EMF. All right, every second, so 0.6. Let me see anything wrong. 190 times 6.0. Yeah, it's about 1100, right? All right. Oh, it's a huge voltage. Okay, number 6. An ideal solenoid has a self-inductance L. Okay, if you now double its radius, okay, this is a 0.6.0. So this is 6.0. Okay, not 0.06. Okay, so in this case, yeah, it's 1100. So 6.0 times it's a 6.0. Sorry about that. 6.0, right? It's about 1100. All right. Okay. Number 6. An ideal solenoid has so this is your inductance. If you now double its radius and its length, but do not change the number of coil, what will its self-inductance? All right, so here's inductance equal to, okay, so it's mu naught N square LA. All right, so everything's here. Inductance depends on proportional area, right? So you see how many things you change. If you double its radius, double radius to 2r, right? Area increased. You see A equal to pi r squared. If you double the radius, A became 4 times big, right? So you increase A by 4, right? Area by 4, and its length, if you double its radius and its length. So L here increased by 2. Okay, so bottom 2, top by 4, bottom by 2, right? Do not change the number of coil. N is the same. What is self-inductance? Okay, so top increased by 4 times, bottom increased by 2, so end up with 2 times, right? So double it. Number 7, a transformer is a device used to, okay, so a transformer, change voltage, change current, and also transformer is used for AC. So this guy doesn't work. Increase or decrease an AC voltage, that's good. Increase or decrease a DC, no. Anything DC associated with DC is wrong. Transfer a DC, okay, all right. So you see, this only for AC. Number 8, as shown in the figure, a straight wire. So this is a straight wire carries a steady current I. A metal bar is in contact with a pair of rail and is in upward motion with velocity. Okay, so this guy move up. The polarity of the induced EMF in terminal X and Y is, all right. Okay, so let's see what we have here is, you see, assume this is connected, right? You basically look at the current direction and you can figure out what is induced EMF direction. You see this current down, use your right hand rule to figure out the magnetic field, right? So right hand rule, number 2, current down, then magnetic field, this side get into the screen, this side coming out of screen. So you have coming out of screen of the field here, and this guy is moving up, which means flux increase. Okay, so changing flux will be in this direction. Induced magnetic field will be opposite to changing flux, will be get into. So this is induced magnetic field. How to make the induced magnetic field this direction? Okay, get into screen, right? So you must have current goes this direction. Current goes this direction. You see, current goes this direction, which means you have, this is positive, this is negative. Okay, so that's the only way. Okay, so X is positive and Y is negative. Okay, just consider this is connected, right? And then you see this is current direction. So current goes this way, so you have induced magnetic field get into screen. Okay, so you should right hand rule number 2. Okay, so that is the direction of the current. Actually, this is also direction of the EMF, and to make that kind of current, you have to have X is positive and Y is negative. All right. Number 9, a coil lies flat on a horizontal tabletop. Okay, flat, and in a region where the magnetic field points straight down. Okay, so magnetic field points straight down, right? The magnetic field disappears suddenly when viewed from above. What is the direction of the induced current in this coil? All right, so magnetic field going down, right? So this is from, you view from top. Magnetic field going down, suddenly this guy disappeared. Okay, so what's the changing flux? You see, initially flux get into no flux, right? Then suddenly no flux, then changing flux will be coming out. Okay, so this is changing flux. Okay, all right, so that you can make the flux disappear, right? Okay, changing flux this way. So induced magnetic field will get into screen. So induced magnetic field. Okay, to make this kind of induced magnetic field, so you have current, right? Current must be in, okay, so in this direction. Okay, so this is induced field, so this is induced current. Okay, so induced current, use right hand rule number 2. This is the current direction, so you see field will come in, let me see, no, I'm sorry. This is the get into the screen, right? So current will be this way. Current will be this way. So current go this way, so get into. So you make this. So this is your induced current. You see current go this way. So you make the magnetic field, this part get into the screen, other part coming off screen. You see current go this way. You see you make this part of this part field get into, and then that part coming out. Okay, so same thing here, right? You see current, right? So right hand number 2, current direction, get into, coming out, right? So current will be clockwise. All right, so yeah, that's all for this quiz 23, chapter 23.